Alright, here we go with linear algebra. So in the words linear algebra, there's of course the word linear, and we will talk about linear equations first in chapter 1. And when we hear linear equations, we might feel like this is very easy, and why is linear algebra complicated if it's algebra about linear equations? Well, the thing is, in linear algebra, what we're going to do over the semester is study linear behaviors, but the objects that we will work with will be various, and typically they will be very abstract. And when we talk about linear algebra, it means, like you can imagine, that with a certain object, let's call it x, you can do a times x, and maybe you can add another object y, so a times x plus b times y plus c times z, etc. But these objects that I called x, y, and z here are not necessarily numbers. They can be anything. So for example, if my first object is a quadratic function and my second object is a logarithmic function, then I can study what happens if I do a times the quadratic function plus b times the logarithmic function. And as we will see later on, we can use very many different mathematical objects, and what we do in linear algebra is to look at what behaviors are common to all these things. So if I do a times an infinite sequence plus b times another infinite sequence, what is the behavior and what is similar to when I do a times a quadratic plus b times a quadratic function. So in the very beginning, we're going to look at linear equations where x, y, and z are numbers, but very soon we will go to very different things. So linear systems, I am not expecting anything to be new to you in this very short section. Firstly, one of the objectives is to be able to solve systems of 3 equations, and then we will talk about the number of solutions to a system of equations. And then we will have one simple example of applying it to a real-life situation. So if we have a system of equations like here, we know from multivariable that these represent 3 planes: x plus 2y plus 3z equals -3, x plus 3y plus 2z equals -6, 3x plus 2y plus z equals -9. Now these planes may have various inclinations with the xy planes, and if they are all in sort of different directions, there's going to be one point of intersection. And the question here is, what is the point of intersection? To figure this out, we solve this. We can use addition or we can use elimination. Here we're using addition, so equation 1 minus equation 2 yields -y plus z equals 3. But if I do 3 times equation 1 minus equation 3, I get 4y plus 8z equals 0. And that allowed us to completely eliminate the x from the equations, and now we have a system of 2 equations with 2 variables. So we can once again use elimination. So from 4y plus 8z equals 0, we can write y plus 2z equals 0, and then if we add this one and that one, we get 3z equals 3, so z equals 1, y equals -2, and x equals -2. Therefore, the point of intersection is -2, -2, 1. So, there are different ways that planes can intersect in 3 dimensions, but really the number of solutions to a system is going to be limited to 3 cases. Either there is just one solution, just like we saw above, and this does not necessarily mean that the 3 planes are perpendicular like they look in this sketch, but simply that none of them is parallel to the others or any other special case. But among the other possibilities, if there's not one solution, then a system of equations can have 0 solutions, and in the case of 3 planes, it means that they can either be all parallel, or maybe 2 of them are parallel and the third one doesn't matter, or this is an interesting case. None of the planes are parallel, but they kind of form a triangle in the middle, so there is no place where the three planes meet. These two planes meet on a line that is shown here. It's like we look at it from the intersection, so we don't see the line, we just see a point. These two planes intersect here on the line, and those two planes intersect on the line, but nowhere do the three planes intersect. Finally, there's also the situation where two planes would be overlapping. It's the same, even if the equation doesn't appear to be exactly the same, like x plus y plus z equals 1 and 2x plus 2y plus 2z equals 2. It's the same plane, two equations for the same plane, and the third one somewhere else. So again, there's no solution to the system of three equations. There's no point that belongs to the three planes. Finally, the last case, so 0 solutions, 1 solution, and the last case is infinitely many solutions. And that can, for example, happen if the three planes share a line. Now, the infinitely many solutions are all the points on the line that is shared by the three planes. Or you could have two planes or two equations that represent the same plane and another one that goes across, and once more these solutions are all on the line of intersection. And finally, the last case is if the three equations actually represent the same plane, and so all points on the plane are solutions. So for the sample application to real life, we are going to look at the analysis of a network. The total flow into a junction is equal to the total flow out of the junction. Set up a system of linear equations representing the figure here. So this could be maybe some kind of electricity map, or it could be just streets and intersection with cars going in different directions. What's important is to understand that nothing stops at the nodes. If 600 cars are entering here, then it means 600 cars are going out either along x1 or along x3. And if we set up an equation for each of these nodes, we will have 600 equals x1 plus x3. For this node, everything that comes in has to be equal to what goes out, so x1 equals x2 plus x4. For this node here, what goes in is x5, so x and x2, so we have x2 plus x5 equals 500, etc., etc. So we end up with a system of 6 equations, but as you can see, there's actually 7 unknowns: x1, x2, x3, x4, x5, x6, x7. So most likely, even though we're not solving it here, this system of equation has infinitely many solutions. But maybe not. Maybe it has 0. But if all these numbers were drawn randomly, then there would probably be infinitely many solutions. So that's it for this introduction, section 1.1. Thanks for listening.